This is problem 1015. It's on page 520. A straight bevel gear pair has the following data. Number of teeth on the pinion 25, number of teeth on the gear 50, diametral pitch 10 inverse inches, and a 20-degree pressure angle. If the gear pair is transmitting 3.5 horsepower, compute the forces on both the pinion and the gear. The pinion speed is 1250 RPM, face width is 0.7 inches. Compute the bending stress and the contact stress for the teeth, and specify a suitable material and heat treatment. The gears are driven by a gasoline engine, and the load is a conveyor providing moderate shock. Assume that neither gear is straddle mounted. So extracting the information from the problem: pinion teeth 25, gear teeth 50. So it's a 2-to-1 ratio. Diametral pitch 10 inverse inches. Let's see, 20-degree pressure angle, 3.5 horsepower. Pinion speed 1250 RPM, and face width 0.7 inches. The conveyor is moderate shock and the driver is a gasoline engine. That essentially just gives us the overload factor. So rather than writing down those two bits of information, I'm simply going to go and look up the overload factor. Now, the overload factors that are used for bevel gearing are the same as the ones used for spur gearing. So all we will do is go back to chapter 9 and find the overload factor. So basically it's just bending stress, contact stress, and material and heat treat. So we don't need the problem statement anymore. So let's go back to chapter 9 and spur gears and look up the various factors, because as usual most of the factors are reusable. Basically they're used for both spur gears, helical gears, and whatever else we need. So let's see, page 338 has the overload factors on it, and it's table 9-7 is the one we need. In table 9-7, basically the power source, it will probably provide moderate shock. If you go back one page to 337, there are descriptions. Let's see, multi-cylinder engine is moderate shock. We don't know if it's multi-cylinder or not, but that's the worst that we have in this table, so we'll have to go with it. And we were told that the conveyor provides moderate shock as well. So the overload factor, in short, is 2.0. If you look at table 9-7, page 338, you'll see where I got the overload factor. Okay, so why don't I just write down the two equations that we need. We need contact stress and bending stress for the bevel gears. And so that is page 397 has the bending stress equation. The one we'll use is 1014. The contact stress equation is the next few pages, but let's copy this one down to begin. So the stress is tangential load, diametral pitch, face width, geometry factor, overload factor, size factor, alignment factor, and velocity factor. Notice there's no rim factor in this equation. That's because bevel gears don't have rims typically. So that is not needed in our equation. A couple of things are different. Let's see, the size factor is different, and the alignment factor is different. So let's go ahead and calculate those two while we're right here. Page 397, the size factor is 0.4867 plus 0.211 or 2133 times, divided by the diametral pitch. And so let's just plug in the diametral pitch, which is 10. And so 0.4867 plus 0.02133. would give me a size factor of 0.508 or so. And then for the alignment factor, Km, go to page 398, excuse me, 399. Equation 1016 says that the alignment factor, Km, is Kmb. Now, if you look below the equation, you'll see it says where Kmb equals, and there's several different options. Both gears straddle mounted, Kmb is 1, but in our case, neither is straddle mounted, and so Kmb is 1.25. So 1.25 plus 0.0036, going back to equation 1016, times the face width squared. Now, of course, the face width is 0.7. So if we plug all of that into the calculator, what do we get? I think I copied that down wrong. 0.0036. There we go. Okay, so 0.7 squared multiplied by 0.0036 plus 1.25 is 1.252 or so. So there's the overload factor, size factor. You know what, rather than doing that, I'll just write them down below. So the let's just do it this way. Size factor 0.508. Alignment factor Km 1.252. So let's see, we've got the overload factor as well. Of course, I've already written that down as 2. The velocity factor, in the text they mention that the velocity factor can simply be used from the spur gearing. Let's see where that's at. Let's see. I don't recall where it's at, but, oh, here it is. Dynamic factor on page 399 under the heading of dynamic factor on the left column. I use the same chart as for spur gears, so basically figure 920. So rather than going through and actually calculating the velocity factor, I'm just going to go back and read it off the figure. So figure 920 is on page 345, but you'll notice that to calculate the velocity factor, we actually need the velocity itself, the tangential velocity. So that's the pitch line speed. Okay, so let's calculate the pitch line speed to begin. This is basically just tangential velocity, v sub t. And we can calculate that from the diameter of the pinion or the gear. It really doesn't matter. We have the speed of the pinion, so let's go for the pinion. So the diameter of the pinion would be equal to the number of teeth on the pinion divided by the diametral pitch, number of teeth on the pinion, 25 diametral pitch, 10 inverse inches. And so that's 2.5 inches for the diameter of the pinion. We'll need that because the equation would be pi over 12 multiplied by the diameter of the pinion times the speed of the pinion. And so these numbers would be 2.5 inches, and then the speed is 1250 RPM. Now, of course, the conversion factors change this so that we end up with feet per minute for our units of velocity. And let's see, plugging it in, pi times 2.5 times 1250 divided by 12 is 818 feet per minute or so. Now, as I said, instead of actually using the equations to calculate the velocity factor, I'm going to go to page 345 and just read it off the graph. I've got the wrong page. Let's try again. How about 341? Okay, page 341, 818 feet per minute. We have to decide on a quality of gearing as well because we have to know what curve we're on. If we look at the suggestions for the quality of gearing, page 330, the particular application we have here let's see, is that it's a conveyor. So the conveyor is the application, and for conveyors, let's see if they have conveyors here in this list on page 330. Let's see. I don't see it in there anywhere. Don't remember what I selected before. Let me look at my notes. I chose a quality of 7. Why, I don't remember, but the only thing listed here is a printing press. And I guess I was thinking that's sort of, but that really doesn't match. A printing press is more accurate than a conveyor usually, depending on the particular conveyor. But anyway, A7 is okay. It's probably a little better than what's needed, but we'll go with it. So I'm going to choose a quality of A7 or so. And then now finally we can go to page, I lost it. Page 341. With our quality of 7, we can look up 818 feet per minute on the x-axis and read off the velocity factor. Now it looks to me like the velocity factor is right at 1.12 or so. And so I'm not going to read that off any more accurately. I'm not going to bother with the equation. I'll just leave it there. All right, now to get the rest of what we need, we'll have to have the tangential velocity. Now the tangential velocity is the same on the pinion as it is on the gear. On a bevel set, the axial load on the pinion is the same as the radial load on the gear, and the radial load on the pinion is the same as the axial load on the gear. So, but mainly what I'm interested in is the tangential load. So let's get the tangential load. We'll get the geometry factor. In fact, it's probably good to just go ahead and get the geometry factor while I'm right there close. Geometry factors for bevel gears are given on page 399 in figure 1015. And the way this works is you start off on the y-axis, which is a little bit different. Number of teeth in gear for which geometry factor is desired. Well, let's get the geometry factor for both the pinion and for the gear. The pinion has 25 teeth, so we'll have to go on the y-axis to 25 teeth and then go over to the number of teeth in the mate. The mate for the pinion is the gear, so we need to go over to the curve for 50. When you do that, looks like the geometry factor on the curve for 50 would come out to about, let's see, that's 0.2456, so each one of these must be a half. I've lost my place. 25 over to 50. There we are. Looks like about 0.255 or so for the geometry factor. 0.255 for the pinion geometry factor. The gear geometry factor will have to go up to 50 on the y-axis and then over to the curve for 25. So the curve for 25, there it is. Looks like that's right at, let's see, 215, 217 or so. So the geometry factor for the gear is lower than the geometry factor for the pinion. I'm sorry, yeah, it's lower. And what that's going to do is actually make the stress on the gear larger, which seems counterintuitive to me. Let me think about that for just a minute. I did read it off properly, so it is what it is. Okay, now notice this is only good for a shaft angle of 90 degrees, pressure angle of 20 degrees, and so that works out. We are using a pressure angle of 20 degrees, and I assume these are 90 degrees to each other, these two gears or shafts. So that takes care of the geometry factor. What else do we need? We need the tangential load. So let's go get equations for the tangential load, and then we should be able to estimate the bending stress. Okay. The tangential load, now in the text, you'll notice page 390, there's a calculation for the tangential load, W sub TP. It's in equation 1010. Now this equation involves the mean radius. Now the mean radius is not at the center of the tooth in a bevel gear set. However, even further, this WTP that's calculated in 1010 is not the tangential load that's actually used in the stress calculation. So what we have to do is use more of a normal equation for W sub t. And that's just the tangential load, or excuse me, we could calculate it as the torque. Let me make sure I've got that right. I'm thinking that we should just use normal calculation for W sub t. Here we go. Page 397. So the WT we plug in is not the one using the mean radius. Instead, it's the equation that we normally use. Probably the easiest one in this case is, it's not listed, but it's just 33,000 multiplied by the horsepower P, which is 3.5 horsepower, divided by the tangential velocity, which is 818. Now, if you plug all that in, you'll end up, since the 3.5 is in horsepower and the 818 is in feet per minute, you will end up with a load in pounds. So I've still got the 818 plus change, so I'm going to invert it, multiply by 3.5, and multiply by 33,000. And I come up with 141 or so pounds force for the tangential load. So now I've got everything I need to calculate the estimate for bending stress in the pinion and the estimate for bending stress in the gear. Notice they're different because the geometry factor is different. So that's just a check mark I erased it. So since the geometry factor is different, we'll get different results. So let's start off. W sub t is 141. I've still got that in the calculator. Multiplied by the diametral pitch, which is 10, divided by the face width, which is 0.7, divided by, let's start with the pinion, 0.255, multiplied by the overload factor, which is 2, multiplied by the size factor, 0.508, multiplied by the alignment factor, 1.252, and then multiplied by the velocity factor, 1.12. Okay, plugging all that in, it looks like the bending stress estimate for the pinion is 11,267. I'm going to round that up to 11,300. For the gear, let's see, if I multiply by the geometry factor for the pinion and then divide by the geometry factor for the gear, it looks like the stress estimate on the gear is 13,241. I'm going to round that up to 13,300. And notice both of these are PSI. So there's the bending stress estimate for both the pinion and the gear. Okay, I'm going to jot down some of the results off to the side because we may need them later. The tangential velocity is 818 feet per minute. Diameter of the pinion, 2.5 inches. Geometry factor for the pinion, 0.255, but I don't believe we'll need these again. But we have them anyway. Let's see, also the tangential load, we'll need that. That's 141 or so pounds force. Okay, so now we've used all of that. Now we need the estimate for the compressive stress. And the estimate for the compressive stress uses a different equation than before. It also has some unique factors in it. So if you'll open your book and go to page 401, you'll see equation 1019. That's the equation we want to use. It's CP root W sub t, the tangential load, overload factor, alignment factor, velocity factor, and then two other factors that we will describe, divided by face width, the diameter of the pinion, and the geometry factor I. Since we just found geometry factors J, let's go and find the geometry factor I. Go to page 403. It's just one page over from where we are. Again, you'll read this off the same way we did the geometry factors for the bending stress estimate. So we'll start on the y-axis, go over to the curve for the number of teeth in the mate, and then go down. But in this case, we're only going to have the pinion geometry factor. So number of teeth in the pinion, we've got 25. So that's one of the major division lines on the y-axis that's not labeled. It's between 20 and 30, halfway between. The number of teeth on the gear is 50. There is a curve for 50, or for the number of teeth 50. And so it looks like we've got about 1.5 minor division lines. And so looks like each minor division line is 1,000. No, that's not right. Each minor division line would be 2,000s. So 1.5 division lines would be 3,000. So 0.083 or so should be the geometry factor for the compressive stress. Let's see, so what do we lack? We've got all of those. All of the other factors are the same. The velocity factor, the overload factor, the alignment factor, all those are the same. But what's different is all these C values. So CP, for example, has to do with the materials that these are made from. We're supposed to specify material. Now looking at these bending stresses, these aren't terribly high, but they're not extremely low. So I would be hesitant to use a brittle cast iron, for example. I might consider a nodular or ductile cast iron for this, especially since the surface characteristics, the compressive stress characteristics that cast iron can take are pretty good. So let's start off assuming we're going to have a cast iron pinion and cast iron gear. Of course, this is up to us as the designer. Since this is a conveyor system, it may not be such a bad idea. Cast iron should work fine. So let's go back and find CP. And that's in chapter 9. It's in here somewhere. Find it in a moment. Still becoming familiar with this version of the book. Okay, I must have missed it. Try again. It's always used in the compressive stress estimates. Okay. What am I doing wrong here? I know it's in this chapter. Here we are. Opened right to it on accident. Page 344. The elastic coefficient CP. If we're going to deal with nodular iron or ductile iron, basically on ductile iron, then CP is 2050. And the roots, or the units are root of PSI, essentially, roots of pounds force per square inch. So that's on page 344, and I'm assuming then that I've got ductile iron for both the pinion and the gear. So that takes care of CP. We need CS and CXC. So let's determine how to figure those out. CS, the size factor for contact stress, is different from the value of KS for bending stress. The factor is based on the face width. For a face width less than 1/2 of an inch, use CS equals 1/2. For more than pi, essentially, use 0.83. Between the limits, which of course we are between those two limits, use a size factor CS equals 0.125 times the face width plus 0.4375. So let's see, the face width is 0.7, so 0.125 times 0.7 plus 0.4375 is 0.525. So there's the size factor. Now let's take care of CXC. CXC, the crowning factor for pitting resistance, accounts for the contact pattern between the mating teeth. Typical bevel gear production processes create crowning both along the tooth flank and across the full width of the face. I'm reading on page 402, second column at the end. This is the preferred approach. Some bevel gears are not crowned, and so the standard recommends the following factors. If the teeth are properly crowned, then we should have 1.5. So I'm just going to specify crowned teeth so that CXC will end up at 1.5, 1.5 essentially. Okay, so now to calculate the contact stress estimate, we just have to plug everything in. So let's see, tangential load, 141 pounds. Overload factor, 2. Alignment factor, KM, 1.252. Velocity factor, same as before, 1.12 there. Size factor, that one is different, but we've got it. It's 0.525. CXC, we specified beveled teeth, so, or excuse me, crown teeth on the bevel gear. So that's 1.5 divided by then the face width, 0.7 divided by the diameter of the pinion, 2.5 inches, divided by the geometry factor, 0.083. So I've got everything that goes in the square root. Now I will take the square root of that result and multiply it by CP 2050. So the result is 94,919.7. I'm going to round that up to 20. In fact, I'm just going to call this about 95 KSI. So there's the compressive stress estimate. Now let's go back to the table for nodular iron, or for iron in general, and see if this is a reasonable design. Are we in the ballpark or not? Now in chapter 9 there is a table that gives you some strengths of cast irons and ductile iron. So page 333 is where I'm at. Table 9-6 is my table of interest. And you'll notice that all of the allowable bending stresses are twice this or so. We don't even have to bother with the cycle factor here. Cycle factors usually come out relatively close to 1. So for any decent number of cycles, which this would definitely see, we're going to assume it's conveyor, it's going to have a 20,000 hour life. It's going to end up in the range of, on the right of the cycle factor chart. I won't even bother concerning myself any farther with the bending stress, because if I'm choosing nodular iron, there's plenty of allowable bending stress. So that part's done. The contact stress, on the other hand, we have to move up to 120-90-02 quenched and tempered, because the one just above that under nodular iron is only 92 KSI. We've got 95 KSI or so. So now I am a bit concerned because the cycle factor may bump this number up enough where iron wouldn't work. So let's find out. Let's find out if that's the case or not. So basically the iron that I think I want to use is, or has an allowable stress of 103. So let's just temporarily note that we want to use nodular iron. The particular alloy is 120-90-02, quenched and tempered, so Q and T. And that it has a strength, an allowable compressive strength, SAC, of 103 KSI. So we're pretty close. Now let's go find the cycle factor. Let's see. The cycle factors we use here they've got CL for case carburized, and most of the bevel gears would be case carburized, but in the case of cast iron, of course, or iron in general, that would not be the treatment, because the case carburization is for steel gears. So let's go back and look for a cycle factor from chapter 9, basically. That should work fine. So page 347, we want a pitting resistance stress factor, stress cycle factor, Zn. And so we need to calculate the number of cycles. We can do that easily enough. I'm going to assume that the life of this set will be 20,000 hours, as is normal for general industrial machines. And of course, number of engagements per revolution would be 1 for the teeth. So the life in revolutions, or the number of cycles on the pinion, because that's going to be the critical one really. The number of cycles is, now this is not the teeth on the pinion, this is the number of cycles on the pinion. It would be the life 20,000 hours multiplied by 60 minutes per hour. That takes care of the hours, multiplied by the speed of the pinion, which is 1250 revolutions per minute. And so now we have the life in revolutions, and there's just 1 engagement per revolution, so no need to add that in. But really we want the life in engagements of teeth. So if we take 20,000 multiplied by 60 and multiplied by 1250, then we get 1.5 times 10 to the, let's see, 3/69. Okay, so that's how many cycles each tooth on the pinion is going to see in its lifetime. So now if we look for 1.5 times 10 to the 9th on page 347, then it appears to me that the cycle factor is a little bit below 0.9. I'll just call it 0.88 or so to have sort of a worst case scenario. I'm not going to go through the equation and bother with it. I'll just say Zn is approximately 0.88. That should be good enough. And basically what this does is it derates the strength. So SAC prime would be 0.88 multiplied by 103. So 0.88 times 103 KSI. Now we could include a reliability factor and a safety factor. I'm not going to bother with it. And so now this comes out to 90.64 KSI. And we've got a problem. So what do we have to do now? Well, now we have to go back, because we'll have to choose something different. Okay, this won't work because the allowable stress is not high enough. So we've got to go back and realize nodular iron is not going to work for this. So we'll have to have a different CP. So let's take steel on steel, for example. And if you go back and you look up on the chart for steel on steel and you look up CP, you'll find that for steel on steel the value of CP is 2100. No, I'm wrong. I'm thinking of a different material. Steel on steel is 2300. Instead of 2050 like we had before for cast iron. That's going to make this number go up a little bit. So let me take the 94,920, divide out the 2050 CP I had before, and multiply in the 2300 CP that I have now. So now my estimate for stress, since I'm going to use steel on steel, is about, I've got 106,495. I'm going to call that 107 KSI or so. So now what? Well, the number of cycles is still the same. Still have the same cycle factor. But now, instead of going and selecting a material and looking up its SAC number, that would be inconvenient, right? Because I'd have to keep multiplying it by the cycle factor to see if this number is above this number. So instead, what I'll do is I'll just bump up this number by this factor. So basically, I will divide the 107 KSI by the cycle factor, 0.88. And in fact, actually, no, that's wrong. that will not be the right cycle factor anymore, because now I'll probably have to end up using case carburized gears, which is normal, as I said, for bevel gears. So actually what we'll need to do is use the cycle factor that's on page 404. Now remember, we had 1.5 times 10 to the 9th cycles on the teeth. So if you go to page 404, look at figure 1020. Last time I did not calculate the cycle factor, this time I'm going to. But it's CL, because it's a different curve for case carburized. So CL equals 3.4822. Number of cycles to the negative 0.0602. Now remember, the number of cycles was 1.5 times 10 to the 9th. So 1.5 E9 to the power of negative 0.0602, and then multiplied by 3.4822. Gives me a cycle factor of 0.976 or so. Now basically what I'm going to do is divide the 107 KSI, let's get for this because we're not using iron, divide the 107 KSI by 0.976, so just invert, multiply by 107, and I get about 109.6 KSI. I'll just go ahead and round that to 110 KSI. Let me move this a bit. Now this is the allowable contact stress that I need. I need to look for at least this much. So really, it should be greater than or equal to 110 KSI. Okay, now the other question is, how hard should it be? Well, let's find out. Go to page 405. And with an allowable contact stress number of 110, you'll notice on the y-axis, we'll have to go from the y-axis and read over. I'd like to use grade 1, because grade 1 is cheaper than grade 2 steel. Here's 100, we'll go to, let's see, 105, 110. And that's pretty close where I could read off about 250. It's a little more than 250. So HB 250 is what I'm looking for. So now I need a steel that can be hardened to that level and that can take the stress that it will be presented. So go to the back of your book to the appendices and look up the steels on page 725. Or actually, wait a second, we're talking about carburized steel, not true hardened steel. So not 725, we'll go over a couple of pages. There we go. Page 729 has the numbers we need for carburized steels. And let's see, we need something that can take 14,000 PSI or so. The yield strength here are all well above that number, so I'm not worried about that one. I'm just looking for something that can be hardened up to the level of 250. There's many options. The second line, 1020, SWQT 350 should work fine because its HB can go up to 255. So we can harden it up to that level. In fact, it probably is that hard in any case. So 1020 SW, single water quenched and tempered. And so that's our specification. That we want. And let's see, anything else? Crown teeth, of course. So we have all the specifications we need in order to order the gears now.